Okay, let's get going on chapter 8. So, chapter 8 is on sequences and series, and probably new to you if you haven't studied much of this before. Sometimes they do this in high school math. And then we get into the last section that we're going to get into is called mathematical induction, and that's the last thing we will leave off on. So let's go ahead and talk about and define a sequence. So the first thing we talk about is a sequence in 8.1. So here's the definition. So a sequence is a function whose domain, the inputs, right, is the set of positive integers. So the natural numbers. So 1, 2, 3, 4, 5, 6, 7, etc. So usually instead of x, we use the letter n, because you have distinct values you're inputting. With real numbers, it's a continuum in between all the numbers, nice and smooth. Well, this isn't smooth. It bounces like that. 1, 2, 3, 4, etc. You may start at 0. That's okay. We define it like this to begin with. And then in other type of classes, you can even go negative. But the general idea of a sequence is that they are integers. Okay, and we'll be using positive integers starting at 1 most of the time. All right, so for example, let's look at a function we've used a lot of, and that is functions x squared. So f of x is equal to x squared. So let's use that function. We've looked at that a lot. And the inputs then, though, are just 1, 2, 3, etc. 4, right? You keep going. So the output, when you square it, is just 1. This should be 4. Okay, I'm not sure how I messed that up. And then 3 squared is 9. All right, so your ordered pairs then are 1, 1, 2, 2. It'd be 3, 9 way up here. And so it's not very interesting, in the between negative 4 and 4. I mean, you just get basically these two values and it's off the screen. Okay, so we're not so much as interested is the graph. Those other functions we like to see what the graph does, that kind of thing. But for this, it's more what's happening to the sequence as it approaches infinity. So normally we don't use the notation f. We use this notation. So we write the sequence f of n is a sub n, or we use b sub n, sometimes c sub n. And so the subscript here, that n, acts like the input of the function, and we call that an index. So for this one above, a1 is 1, a2 would be your 4, a3 would be your 9. And so really this is how you write out the sequence. 1, right? 1, 4, 9, 14, 16, 25, right? You'd be squaring all those numbers. So that's the sequence. Sequence is squares, basically. Some other notation we'll look at looks like this. So let's look at this example. At any time, you may want to try these if you kind of know what's going on. But the first few things here, I'm just going to have it written up and talk about it as we go. So you will want to pause and write stuff down. So write the first 4 terms of the sequence. So sometimes we write, when you have this notation, looks like a set notation. You don't say the set of, you say the sequence a sub n. And so a sub n, so a sub n, do I have that later? We call that the nth term. So the general term is called the nth term. So let's write that down. A sub n is called the nth term. So it's like saying that's the function. So the nth term of the sequence is really basically defining the function explicitly. All right, so then here's your function a sub n, and then you just plug in values. Right where the n is, you put in 1, and then you simplify it. So look at all of those. And so you construct that sequence, 0, 1/2, 2/3, 3/4. Okay, next one. B sub n is this form, -1 to the n plus 1, and then it's 2 over n. So what happens there then is as you put in values of n, right? N is, again, your domain starts at 1. Here's your domain up here. What's going to happen to this negative? When you do n, we put in 1, you get -1 squared. What happens to that square? It becomes positive. And when it's odd, it becomes negative. Even, positive. See how that works? So that's alternating. So this is called an alternating sequence. Okay, so you get 2, 2/3, 2, -1, positive 2/3, -1/2, etc. Okay, so that's the idea of a sequence. Moving on to more definitions. N with an exclamation is not like n, it's not that. It's actually n factorial. Usually in class I like to yell loud, but it doesn't work when I'm recording a video. So n factorial is defined to be this. You take whatever number it is, like 6, and then you subtract 1 each time until you get down to 2, 3, 1, 2, 1, right? In that order. So 6 factorial is 6 times 5 times 4 times 3 times 2 times 1. If you multiply it out, you get a large number. A couple definitions. These are definitions over here. I meant to do that one. So a couple definitions. 1 factorial is 1. 0 factorial is defined to be 1. Okay, so those are straight definitions, what they have to be for everything else to work. Okay, moving along. So when you're asked to reduce something like this, don't just, your calculator has this button usually. All your scientifics have the factorial button, but you really don't want to just multiply factorials. The function factorial grows really fast. It grows faster than exponential functions, in fact. So what you want to do is simplify it. You want to get in the habit of simplifying these things as you go. So you write it out like this: 3, 2, 7, 6, 5, 4, 3, 2, 1, 4, 3, 2, 1, and then you simplify and reduce. So you reduce things out that are going to essentially cancel. They reduce, they don't cancel, right? So all of these are gone right there. Let's change that color. I don't like that color. It's got to be a little more. There we go. Okay, so these are gone. That reduces down. So basically that is 4 factorial. I was trying to see what I wrote there. That is 4 factorial. So that's 4 factorial. This is 4 factorial. That's what reduces. So you want to simplify that first, right? Annihilate those things here and here. And then what you get is just the product of 3 times 2. So now you get 3 times 2 times 7 times 6 times 5. And that's what that 1260 is going to be. Okay, if you have straight variables in there, so not just the numbers, that's when it gets a little more difficult and interesting. So n factorial divided by n minus 2 factorial. Basically, you write out n factorial, the definition. So remember the definition's right here. So it's n times n minus 1 times n minus 2 times n minus 3 times n minus 4, etc. Okay, but once you get down to n minus 2, you could just say factorial, and then it means it goes on forever. So those terms will then cancel out. So this n minus 1 factorial divided by n minus 1 factorial reduces to 1. So it reduces like that to 1. Okay. So instead of, you don't have any factorials anymore. So they're gone. Once you reduce, you just get this form. Okay, moving along. Let's talk about something that's recursively defined sequences. And I like to show this, although for our purposes we really won't use it much. But I do want to show it to you because it does come up if you ever study anything later. Comes up as something you might see, and it's something you may have heard before. Okay, so don't look ahead. Okay, so okay, so let's suppose. So if you have just this, that's what we refer to as an explicitly defined function. Basically, plug in a number, whatever term you want. So if you put in 8. That's the 8th term. You square it and get 64. Okay. So in a recursively defined sequence, we say the previous terms define the next term. Now, it could be the previous 1 term, or there could be the previous 2 terms, or it could be even the previous 3 terms. Those define what the next term is. So let's take a look. So for example, a sub 1 is 1. And let's say a sub n is n times a sub n minus 1. So this is the previous term. So a1 is 1. a2 is we put in the value, right? 2 times the previous. So the previous is 1. You get a product as 2. A3, you put in whatever's here, you put here, times the previous. All right, so study that. Keeps going in that manner. And you get, let's go and highlight some of these. Okay, so this is the previous. All right, so this is the previous term. Let's see how that's working. And then here's 6, here's the previous. Okay, so as you define that, look what you're getting. A5 is 5 times 12. Well, that's 5 times 4 times 3 times 2. A6, previous terms, 6 times 5 times 4 times... What is that defining? What is that? Okay, so this recursively defined form actually is the definition of n factorial. Okay, so it's hard to show it to you when I'm going through this, so you want to spend some time thinking through it, maybe pausing it as I go. And then we will do problems while I write it out. This is just getting started. Save some time for us. So next example, this one maybe you've seen before. Well, the name at least. So a sub 1 is 1. A sub 2 is 1. A sub n plus 2, so not the first or the second. So you start at 1, you're going to get 3. So is defined to be the sum of the previous 2 terms. Okay. So A1 is 1, A2 is 2, A3 is 1 plus 1, which is 2. A4, the next term, will be the sum of the previous 2, which is 3. Then A5 is the sum of the previous 2, which is 5. A6 is the sum of the previous 2, which is 8. So you get 1, 1, 2, 3, 5, 8. That is called a Fibonacci sequence. There's different forms, but that's the basic, the most simple one, basically, is the Fibonacci sequence, which if you look that up, you'll see there's a ton of applications and stuff that comes up in nature for Fibonacci sequences. All right, moving along. Series and summations, series or summations. So that's the sum of the sequence. That's the concept, is the sum of the sequence. So if you have a sequence A1, A2, A3, A4, etc., a series is adding those all up. You basically put plus in between all of those things. And we use the sigma. So we use the Greek letter sigma. Okay, I'll just write it over here. We use the Greek letter sigma. So it's uppercase sigma, and it means basically sum in math for our purposes. All right, so finite sum, you start at the lower limit, it's called the lower limit, and you go to the upper limit. So the variable is here, that's what you're plugging in, substituting in, and that's called the index. You may see I, K, or J, or even N sometimes in here instead. You can even use in. It doesn't have to stop at in. Normally that's what we're doing, I think, in this book. But an infinite sum means you add forever. And that's where you put infinity at the top. That means you never stop. The dots means you never stop. So let's look at a couple examples of that. So write the terms of the sequence. And this time I'm changing it up at 0, just because, to n minus 1. So your terms then, your k is 0, 1, 2, all the way to n minus 1. Okay, so that's what you're going to substitute into the sequence. So 0, 1, 2, all the way to n minus 1. So you just substitute those in, plug them in, and evaluate. And then you get your sequence. Okay, so let's work on these. This is going backwards, basically. This is write the summation notation. Okay, so let's look at these examples. Okay, write the sum using summation notation. So that's what we want to do. So first you got to figure out kind of the pattern. What is it doing? So 1, 4, 9 to 81. What does that look like? Yeah, those look like squares. So it's 1 squared plus 2 squared plus 3 squared, etc., all the way to 9 squared. All right, so then you got to figure out your a sub n. So your nth term, a sub n, or you could put k there if you wanted to, is n squared starting at what? Starting at 1, yes. If you start at 1, then you get n squared. So you say that this is equal to the sum as, and we'll use k here, because that's the index that runs from 1 to whatever value you would need. So this is k goes from 1, and then what gets you that 81? Well, you just 9 squared is 81, so you go 1 to 9. So k goes from 1 to 9 of k squared. Okay, so that would be the sum. All right, let's change the variable here, the index variable. We're going to use I. So we're going to say I is 1, 2, 3, 4, 5. And then what's happening to the sign? The sign is alternating, right? Minus, plus, minus, plus, minus. So what you then would need is, so guess on this one. Take a second to guess. It's the sum. Try that again. The sum. And it's going to be negative 1 to what? And you just either put n or n plus 1. Basically, is all you need to remember to do, really. So the first one needs to be negative. So we'll make that just n. And then the next one will be positive. Oh, you know what? I already said we're going to use I. So we're going to put I up there. So let's change that to I. So I goes from 1 and then to 5. Because I mean, I just listed them all out. It goes 1 to 5. Okay, then what's happening to... So that takes care of the plus minus. Then what? What's happening to that denominator? So the numerator is always the same, 1, 1, 1, 1, 1. So it's a fraction. And then it's the denominator to what power? What's 2, 4, 8, 16? Yeah, it's 2 to the I. So it's 2 to the power. So 2 to the first, 2 to the second, 2 to the third, 2 to the fourth, 2 to the fifth. See that? Try that again. 2 to the first, squared, cubed, 4, 5. That gives you the terms of the sequence. Okay, next one. So try this next one. Write that in summation notation. That one's a little, so the denominator might be a little easy. We'll use K. How about K this time? I guess we used K already once, huh? 1, 2, 3, 4, 5. So that's going to be the sum as K goes from 1 to 5. Nothing alternating. Denominator is easy. It's X plus K, right? I mean, literally just plugging those in here, 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 here. The X stays X. That's actually a variable. That's something else. What's that numerator doing? 1, 2, 6, 24, 120. That's, so if you haven't figured it out yet, that's factorial. That's, oops, that is not n, that's K factorial. So it's K factorial in the numerator. Okay, so then we get properties of summation. So let's go and make this look nice. So let's do some properties of summation. So let A sub n, B sub n be a sequence. We're going to let C be in the set of reals, so it's just a real number. And so you get these properties. So 1, the sum of just C, so you're not plugging anything else, is n times C. And then the sum of C times A sub I means you can just factor out the C. Okay, and the sum of plus or minus A sub I, B sub I, basically you can either sum individual terms that are added together, or you can break it up into individual sums. So here's a little explanation on the proof. So if you had the sum of just C, basically you write C out n times. So that's just n times C. And then you have the sum of C sub I. Basically, C is in every term. So that means you can just factor out that C and rewrite all of this as a summation. Okay, and this last one, if you write each of these terms out, it's A1 plus B1, A2 plus B2, right, etc. You can rearrange, so you can use associative, so it's all just real numbers being added together, essentially. So you can use associative and commutative properties of addition and rearrange it and put it in this form and this form, which is a summation. Okay, so that's how you do it. Now this next example will kind of put some stuff together. So we can do. So take a look at that. See if that makes sense. Take a look at some of the book examples just to get used to the summation. So you want to get used to the summation. If any of you need to go on to or take, in addition to this class, take statistics, you'll see this summation notation a lot. So you want to get comfortable with that, what you're doing. Okay, we'll stop there. That wraps up 8.1 on sequences and series introduction.